All right, guys, here we go. This is, go away, little box. There you go. All right, so this is page 3 now of the Unit 3 test review. So you should have done 1 and 2. Now we're on to some problems. We're past the multiple choice. So this says, assuming no friction, find the acceleration of a 25 kilogram bookcase being pushed by 100 newtons of force. So this looks to me like F equals ma. I'm going to make this a little bit smaller. About that. F equals ma. So I need to identify what each of these things are. So F, M, and A. Now, 25 kilograms. Kilograms we know is a mass, so I'm going to put 25 right there. Newtons is a force, so I'm going to put 100 right there. And then this wants me to find acceleration, so that's my question mark. So all I'm going to do now is I'm going to take and I'm going to put my 100 newtons in place of the F. I'm going to put my 25 in place of the M. And then I'm going to finish this thing out. So I've got 100 equals 25 times A. Now I want to get A by itself. So all I'm going to do here is divide by 25. 25. And then A equals 100 divided by 25, which is 4. Now, we need to make sure that we have a unit on here. Acceleration is always meters per second squared. That's written up on the board, guys. You don't even need to put it on your card. All right, now when a 1,500 kilogram car slams on the brakes apply a force of 7,000 newtons. Calculate the acceleration. So again, this looks like F equals ma to me. So I have my force, my mass, my acceleration. Now, it gives me 1,500 kilograms is my mass, so that right there, that's a mass. 7,000 newtons, that looks like a force. And then acceleration, that's what we're trying to find, right? It says calculate acceleration. So now I'm just going to take my force, put it in there, my mass, put it over here. And I've got 7,000 equals 1,500 times A. Again, I'm just going to divide by 1,500 on both sides. Remember, don't subtract. Divide by 1,500. And then I ran out of space, so I'm going to write A equals, and now I got to do this 7,000 divided by 1,500. I should be able to do this. Yeah. 7,000 divided by 1,500, 4.67. Acceleration, thank you, is 4.67 meters per second squared. That's my answer here. Now, let's look at part B. It says if the car starts out going 40 meters per second, how long will it take the car to come to a complete stop? Now, let's try and figure out what we can use here. Now, we'll move that. The equations from the last unit are written on the board, but you got to figure out which one you want to use. Do we want to use number 1 or number 2? Now, since this doesn't say anything about distance, I'm thinking that it's probably not going to be number 2, because number 2 is all about distance, delta x. So let's try number 1. So my equation is going to be VF equals VI plus A delta t. So let's see if I can come up with these things. VF, VI, A, and delta t. Well, VF is going to be the final speed. So it says that at the end, it's going to come to a complete stop. So I think final speed is going to be 0. Initial speed looks like it says the car starts at 40 meters per second. So I'm going to say my initial speed is 40. Now acceleration is what we got up here, 4.67. So I'll just copy that and paste it right there from our previous problem. Now delta T becomes our question mark. So, and that makes sense, guys. We don't want to have every single one of the variables. We need to have at least one variable that we don't know. That's the whole reason we use equations. So now I'm just going to take them and plug my stuff in. So VF, we said that, uh-oh, let's get that. I don't know why it's not grabbing my 0. There we go. VF is 0. VI is 40. A is 4.67. And then delta T we don't know yet. So I've got 0 equals 40 plus 4.67 delta T. Now, this is going to be a two-step equation instead of a one-step equation. So remember, I'm trying to get delta T by itself here. So first, let's get rid of the 40. I'm going to undo that by subtracting it from both sides. That's going to leave me with negative 40 equals 4.67 times delta T. Okay. Next, interesting. This is an interesting problem. So, realistically, guys, because the car is slowing down, and let's not worry about this too much, but because the car is slowing down, this should actually be negative. If you didn't have negative, that's fine with me. That's not cool. Boo, Mr. Pierce's question. So really, I'm going to change this because this should have been a negative 4.67. If you go through this whole thing and you get a negative number for time, it's fine. Just write it down. Just change it to a positive and you'll be okay. And so we should have a negative 4.67. And so now what we're going to do is we're going to divide both sides by negative 4.67. Negative 4.67. And I'm going to end up with delta T equal to the answer to this part right here. So negative 40 divided by negative 4.67. Let's do that. So let's do 40. Did I do a negative? Nope. Well, we'll do 40 divided by 4.67 because I know that a negative divided by a negative is a positive, and I'm going to get 8.57. So my answer here for delta T becomes 8.57, and that's a time, so it's seconds. 8.57 seconds. Now, if you had done all those calculations and ended up with negative 8.5 seconds, all I'd want you to do there is think to yourself and go, time can't be negative, so I'm just going to erase that and then just leave it as positive 8.5 seconds. Now, we've got two more here. Mr. McSparron has a mass of 87 kilograms. Calculate his weight in newtons here on Earth. Now this, we got to go back to a different version of our equation that said Fg equals mg. Now you should notice that that's the same as F equals ma, but now the acceleration is just the strength of gravity. And so now I've got Fg, m, and g. Well, Fg is what I'm trying to find because I want to find weight. So that's my question mark. Mass is 87 kilograms. That came from right there. And then g is 9.8. That came from right there. So all I'm going to do is go Fg equals 87 times 9.8, and I'll get, let's go here, clear, 87 times 9.8, and I get 852.6. There we go. Fg equals 852.6, and that's a force, so it's got to be newtons. All right, now here's what I'm going to do. This says calculate his weight in newtons on the moon. Well, I know it's the exact same stinking process. Actually, here we'll do this. We'll copy it. We'll paste it. But I know that now, instead of 9.8, I'm just going to use 1.6. That comes from right here. It's the same problem, but with one number different. So now instead of 852, let's go do 87 times 1.6 on the calculator. 87 times 1.6 equals 139.2. And that's what we'd expect to see. We expect to see a smaller weight on the moon than we saw on the Earth. So that was my answer there. That's my answer there. All right. There we go, guys. That's page 2. Now you try out the next one on your own.